Chapter 12, Elementary Chemical Kinetics. Section 12.2, Reaction Rates. It is straightforward to define the reaction rate for elementary reactions. The reaction rate is denoted by R, and R can be the consumption rate of the reactants. R can be the production rate of the products. Here's one example. Hydrogen atoms react with fluorine gas to produce hydrogen fluoride and fluorine atoms. How do we define the reaction rate? Well, the reaction rate R can be how fast the hydrogen atoms are consumed, or how fast the fluorine molecule is consumed, or how fast hydrogen fluoride is produced, or how fast the fluorine atoms are produced. For this kind of reaction with different coefficients, we'll have to be a little careful here, because the production rate of the fluorine atoms is 2 times the consumption rate of the F2 molecule. And therefore, the reaction rate may be defined as this way. It's how fast F2 is consumed, or how fast the fluorine atoms are produced, divided by 2. Again, it's just due to the difference in the stoichiometric coefficients. For complex mechanisms, the ratio between stoichiometric coefficients do not always reflect the instantaneous ratio between the consumption or production rate, but over a long enough reaction period they do, approximately. For example, if we look at the combustion of methane in oxygen, well, we cannot easily define the instantaneous reaction rate. It's just because when CH4 is consumed, we're not really getting one CO2 or one water. Very likely at the beginning of the reaction, when one CH4 molecule is consumed, we actually have a methyl radical and one hydrogen atom being produced. So it's not going to reflect the change of O2 or CO2 or water. However, when the reaction is complete or nearly complete, we can look at the stoichiometric coefficients. And now the reaction rate can be defined as the production rate of CO2 or the production rate of water divided by 2 due to this coefficient. It can be the consumption rate of CH4 or the consumption rate of O2 divided by 2. Again, those stoichiometric coefficients should be used in the expression of reaction rate, and we should use their reciprocals. Again, for example, if let's say 1 mole CO2 is produced, then at the same time 2 moles of water are produced. Therefore, we need to divide the production rate of water by 2 so that this equal sign holds. For convenience, the unit for reaction rate is the unit of concentration divided by the unit of time. This is because concentration is an intensive property, while the amount or the number of moles of a chemical is an extensive property. It's impossible to enumerate all possible values of any extensive property when we are trying to describe how fast a reaction goes. So for example, if you have hydrogen reacting with a fluorine atom to produce hydrogen fluoride and a hydrogen radical, how fast this reaction proceeds Well, if you use the number of moles per unit time, well, then you have to specify the amount of all chemicals. It's an extensive property. It can hardly be tabulated with all possible values. That's why we often use the concentrations and their changes over time to describe the reaction rates. When we use the changes of concentration per unit time as the reaction rate, we often use a non-SI unit in chemical kinetics. It's molar per second. Molar is a non-SI unit. Molar is mole per liter. Mole is the SI unit for the amount, but liter is not. Liter is 10 to the power of -3 cubic meter, while cubic meter is the SI unit for volume. But still, for convenience, we often use molar per second as the unit for the reaction rate. The reason we do not like to use mole per second is this. A reaction in a 1 liter container versus the same reaction in a 5,000 liter container. They may have the same reaction rate expressed in molar per second, but their reaction rates may differ by a factor of 5,000. If the reaction rate were expressed in the units of mole per second. So that's why it's more convenient to use molar per second than mole per second. There are many other units for reaction rate. Another commonly used non-SI unit of reaction rate is molecule per cubic centimeter per second. We can do some derivations to connect this unit to this unit. 1 molar per second is 1 mole per liter per second, and 1 liter is 1,000 cubic centimeter, and 1 mole is 6 times 10 to the power of 23 molecules. Therefore, over here we have 1 molar per second is 6 times 10 to the power of 20 molecules per cubic centimeter per second. When reactions are really slow, we tend to use this unit of molecule per cubic centimeter per second. When the reaction rate is faster or much faster, we tend to use molar per second. Again, for extremely slow reactions, we use this molecule per cubic centimeter per second just for convenience. The SI unit for reaction rate is mole per cubic meter per second, but this is rarely used in chemical kinetics. We can do some conversion here. So 1 molar per second is 1 mole per liter per second, which is 1 mole per 0.001 cubic meter per second, and it's 1,000 mole per cubic meter per second. Also, we can convert this to molecule per cubic centimeter per second. The derivation is straightforward.